Okay, so this is our first lesson in Unit 2, Nuclear Chemistry. For the record, this unit in most high schools is taught at the end of the year of chemistry, but I like to do it in the second unit because it has a lot to do with protons, neutrons, and electrons, and other small particles that are in the nucleus. So I'd like to do it just right after Unit 1. But if you have friends in other high schools, they very well may be doing it just right before the Regents. We will discuss in this lesson the concept of nuclear decay, what it means to be stable or unstable for a nucleus, any risks associated with nuclear decay, and lastly, we'll discuss something called a neutron to proton ratio, which just a little bit of math, but it goes a long way in predicting whether or not an isotope is going to be stable. So we do need to do a Unit 1 exam, item analysis, and look back. I will speak about that in class when I see you next. So make sure you ask me about it. Make sure you ask me about this Unit 1 exam, item analysis, and I'll explain exactly how to get that done. This do now is somewhat somber, but it has been chosen specifically to help us understand the power of nuclear chemistry. So you should pause the video and read the text, and then ask yourself what you think nuclear chemistry is. Okay, so nuclear decay, this is our first topic. I would first point out the big winner on this slide is this awesome diagram that has a bunch of what seem to be neutrons and protons surrounded by a couple of orbits of electrons, and flying through those orbits and out of the atom completely, we have these small clusters of, it looks like, 2 neutrons and 2 protons. Same thing over here. And here. All right, so firstly, the word decay just in general means to fall apart. And in the picture to the right, I think that's exactly what is being shown. The nucleus is falling apart and it's spitting out particles from its nucleus. So here's a definition for you. A nucleus of a particular isotope decays naturally when it is unstable. So unstable basically just means a nucleus that will decay. The product of that decay, I'm actually just kind of referring to these guys right here, or the product of the decay. These are called radiation, or you can refer to it as nuclear decay. So the decay of the nucleus, that's why we call it nuclear decay, or you can just think of them as radiation particles. The reason why we call it radiation actually comes from the same roots as the word radius, and or even a radiator, and it just means to move outward from the center. Different elements decay in different ways. We will get to it much later, but if you are curious, there is a reference table called Table N, and Table N highlights some of the different decay modes that exist. Okay. Poor Brittany. I love Brittany, but there was a time when Brittany was more stable, and there was a time when she was less stable. If you don't remember this, you need to Google this. But stable basically means that you expect something to stay that way for a while. You don't expect it to fall apart. You don't expect it to fall down. That's basically what stable means. Unstable is the opposite. It means that you are expecting things to fall apart. Risks of nuclear decay. You should have a list of some risks of nuclear decay. I will write in some examples as I go, but we'll actually have a much longer list towards the end of this unit. But you obviously have cellular damage. And that just means like damage to, tissues and things that make up living things. Mutation is a risk. We also have ecological poisoning. If the waste products from nuclear reactions get into the environment, that's really bad for the ecosystem. And we also have like long half-lives. I realized halfway through saying that you don't know what a half-life is yet. I'll teach you this unit. But this basically means that if it's toxic right now, it's going to stay toxic for a long time. And other risks of nuclear decay, they can get kind of like strange and political, but nuclear power has a lot to do with wars and terrorism. So like for instance, nuclear power plants are terrorist hotspots. They're like terrorist targets. So there's a short list, and we'll have some more discussion about nuclear decay later. All right, this is one of the big ticket items in this lesson, the neutron to proton ratio. So a nucleon, this is a definition, nucleons are particles from the nucleus. And examples of particles from the nucleus include neutrons and protons. So as I said, the two nucleons that you need to know about are neutrons and protons. Protons and neutrons would have no effect on each other, and that's because the neutron, being neutral, has no ability to attract or repel others electrostatically. Proton versus proton would be major repulsion. Repulsion just means that they repel. And then neutron to neutron would be no effect. So what I've just done here is I included all the options for what can happen in the nucleus between a proton and a neutron, or a neutron and a neutron, or a proton and a proton. And the only one that really has any effect to be noticed is the proton to proton effect, and that is the one that produces repulsion. So if that's the case, if the primary force inside a nucleus is that of repulsion between protons, then one of the things that we should expect to occur is that the nucleus should explode. It should fall apart because of all of the repulsion that's going to be pushing the protons away from each other. So the nucleus doesn't do that. And the thing that prevents them from flying apart and spewing radiation all over the place is another force. And the identity of that force is called the strong nuclear force. That strong nuclear force is a force that attracts particles to each other, and it's much stronger than the repulsion that impels this nucleus to fly apart. So there is a delicate balance of neutrons to protons in the nucleus of a stable atom. And that balance is important because it allows the strong nuclear force to be in balance with the repulsive force of protons and protons. So that delicate balance for many elements is very easy to predict, and that ratio is 1 to 1. Meaning if you are an atom of nitrogen and you have 7 protons because you're nitrogen, and your mass is 14, therefore 7 plus 7 is 14, and you have 7 neutrons. if you compare that to your 7 protons, because you're nitrogen, what you end up with is 1 to 1. This ratio, 1 to 1, is indicating that the nuclide, nitrogen 14, is stable. The one exception that I need to mention is that the 1 to 1 ratio is a method for predicting stability for some elements, but there are many elements that it does not help to predict stability with. So all of the, we can say, beginning elements can be predicted with this ratio. That would be an element like hydrogen or helium, or lithium, or beryllium, or boron. And the elements that I'm naming right now are just the first elements. In fact, the 1 to 1 ratio only works for elements 1 up to 20. I believe 20 is calcium. And then after calcium, the 1 to 1 ratio isn't very helpful anymore, and it does not predict stability. So in short, if you're an element after calcium, let's say you are an element gold. Gold is way after calcium on the periodic table. Having 79 protons would make you gold, but having 79 neutrons, so that it's 1 to 1 ratio, does not make that gold atom stable. So the 1 to 1 ratio, it only works if you're in that small group at the beginning, from 1 to element 20, and that's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Only those. All right, so if you are a living thing and you are too near a source of nuclear decay, you are going to have cellular damage, and maybe mutation of your DNA. All right, so we are in the pair up. We will work on this in class tomorrow as classwork. We'll also have a short review of the lecture. So copy down these questions right here. That'll be classwork for tomorrow. And in addition, the summary, we can do that in part as our exit ticket tomorrow. Thank you guys. Have a wonderful evening.